Hello students, having studied Coulomb's law of electrostatic force, now we are in a position to understand what exactly is electric field. So our next topic is electric field. In order to understand electric field, we must first define source charge and test charge. So what is a source charge and what is a test charge? You know, source charge is something which produces an electric field, and test charge is something which experience an electric field due to a source charge. So we can indicate source charge with the letter capital Q and test charge with the letter small q. Now source charge is something which will produce an electric field. It will produce an electric field, and test charge is something which is going to produce, which is actually experiencing the electric field. It experience an electric field. Now it is very important that our source charge should be very greater than the test charge small q. Why? Because if the magnitude of test charge is large compared to the source charge, then the electric field produced by the test charge may affect the source charge. So in that case, it is very difficult to find out or define an electric field. So now we are in a position to define an electric field. Just like a mass, for a mass, there is a gravitational field around it. A charge has an electric field around it. We already know F equal to m into g is nothing but it is the force or weight experienced by a body. Similarly, on same parameters we can define an electric field by the equation F equal to Q into capital E. Here the term E is nothing but electric field. So we can write down electric field equals to force per unit charge. But this particular definition, force per unit charge, is not precise or apt, because here we have not defined what exactly is small q or test charge. Now in order to take the value of the test charge, we can consider that the value of test charge is very small. So we can take a limit q tends to 0, then we can write down F by Q. So electric field can be defined strictly in terms of small q tends to 0, F by Q. So this will basically give you an apt definition of an electric field. So this actually means that whenever we are talking about electric field, we should consider this test charge to be very small. It is so small that it is not going to affect the source charge capital Q, the source charge capital Q, and test charge small q, which is of course given by F equal to K capital Q small q divided by R square. We can take a unit vector R here. Now we also know, we can give this equation as equation 1. We also know F equals to QE. This is our second equation. Now from both equations 1 and 2, we can write down K capital Q small q by R square equal to QE. So here we can write down this electric field to be K capital Q by R square. Now this particular equation, E equals to k cube by r square, gives the electric field due to a source charge capital Q, and it also tells us that the electric field is not going to depend upon the test charge small q, because it is not connected with the small test charge small q. Now we can also find out what is the SI unit of this electric field. From this particular equation, second equation, we can write down E is nothing but F by Q. So the SI unit of force is Newton, and for charge it is Coulomb. So electric field is nothing but Newton per Coulomb. Students, you should remember that this electric field is a vector quantity. It is not a scalar quantity, it is a vector quantity. Now students, we can also find out how the electric field looks like for a positive charge and how the electric field looks like for a negative charge. For a positive charge, we can draw the electric field. It is radially outward, just like this. It is radially outward. So this is the electric field for a positive charge, and similarly for a negative charge, this electric field will be radially inward. It's just the arrows are towards the negative charge. So this is how an electric field for a negative charge looks like. Here, from this particular equation, we can see the electric field is always going to depend upon the distance r. That is the distance of test charge small q from the source charge capital Q. So with this particular, so here the magnitude of electric field is also going to depend upon r, and hence we say that it is a vector quantity. Now students, we are in a position to find out the electric field due to n number of charges. Suppose we have a system which consists of n number of charges. Say Q1, Q2, let us consider this to be Q2, and this one is say Q3, and another charge Q4. So we have a system here which consists of 4 charges, say Q1, Q2, Q3 and Q4, 4 number of charges. Now these charges are going to produce electric field of their own. Now what is the result of these all electric field, the electric field due to all these 4 charges? We can easily find out the total electric field due to all these forces, all these charges. Okay students, while using superposition principle, we must remember we will take one charge at a time. This means we will try to find out the electric field due to a single charge, and then we try to add all these electric field using superposition principle. For example, for the electric field due to this charge Q1, say this is E1, this is E2, this is E3, and say this electric field is E4. So we can easily find out this electric field due to individual charges. E1 equal to K Q1 by say R1 to P square. Similarly, we can find out electric field E2 equal to K Q2 by R2 P square, and we can of course write down here unit vector pointing from 1 to P. Similarly, we can find out E3 equals to K Q3 by R3P square, unit vector R. Similarly, we can also find out the electric field due to the charge Q4, which is given by E4 equals to K Q4 by R 4P square, unit vector pointing from 4 to P. So here P is nothing but this particular location where the field is acting towards. Now, using superposition principle, we can add all these four electric fields. That is, we can write E is to E1 plus E2 plus E3 plus E4, and we can of course add any number of electric field up to n times if we have n number of charges. So we can just add all these electric field to get the net electric field due to n number of charges. And as we have already discussed that E is a vector quantity that varies from one point to another point in space, and of course it is determined from the position of the source charges. Now students, let us try to understand the physical significance of electric field. Now till now in this chapter you may be wondering what is the need of introducing an electric field. What we really, when we talk about charges, we are talking about the force that is exerted between two charges and what is the force experienced by a test charge. Now what is the use of introducing electric field? Now what is the physical significance of electric field? Now we must understand that when we talk about a system of charges, the measurable quantity is basically the force on a charge, and of course we know that it can be directly determined by using Coulomb's law and of course by using superposition principle. Now basically electric field is a very simple way of characterizing the electrical environment of any system of charges. Electric field at any point, in fact, electric field at any point in space around any system of charges will tell us the force a unit positive charge will experience when it is placed at that particular point. And this means that electric field is a characteristic of the system of charges and it is independent of the test charge that you place at a particular point to determine the field. So basically when we talk about the concept of field in physics, it generally refers to a quantity that is defined at every point in space, and it can of course vary from one point to another point. So the electric field is a vector quantity since force is a vector quantity.